Welcome to this lecture on inorganic chemistry. Today we are going to explore the fascinating world of probability distribution plots. When we study atomic structure, we quickly realize that electrons do not orbit the nucleus in perfect predictable circles. Instead, they exist in a cloud of probabilities. Understanding these plots is absolutely essential because they form the very foundation of chemical bonding, reactivity, and the three-dimensional shapes of molecules. Let us dive in and uncover how we visualize the invisible. Now that we know what we are studying, let us imagine trying to locate a specific bee in a massive swarm flying around a beehive. You cannot point your finger and say exactly where that bee will be in the next split second because it moves too fast and unpredictably. However, if you take a million photographs over time and overlay them, you will see a dense cloud of dots near the hive that gradually thins out as you move further away. In atoms, electrons behave in a very similar way. Because of their wave-like nature and the uncertainty principle, we can never pinpoint an electron's exact location. Instead, we use probability distribution plots to map out the regions in space where an electron is most likely to be found. Building on that swarm analogy, we need a mathematical way to describe this behavior. In quantum mechanics, the behavior of an electron is described by a mathematical expression called a wave function, denoted by the Greek letter psi. While the wave function itself does not have a direct physical meaning that we can measure, squaring it gives us something incredibly useful. The square of the wave function represents the probability density. You can think of probability density as the exact chance of finding an electron in a tiny, specific, pinpoint volume of space. But to understand the whole atom, we need to look at how this probability changes as we move outward from the nucleus. This brings us to the mathematical core of our topic. To understand how probability changes as we move outward, we use the radial probability distribution function. This formula calculates the total probability of finding the electron anywhere within a thin, hollow spherical shell at a specific distance from the nucleus. In this equation, capital P is the radial probability. The variable r is the distance from the nucleus. Psi squared is the probability density we just discussed, and dr is the infinitesimally small thickness of the shell. Notice what happens physically. At the exact center, where r is 0, the probability is 0. As distance increases, the shell volume grows, but the wave function eventually drops towards 0. This competition creates a peak, showing the most probable distance to find the electron. Now that we have seen the formula, let us understand exactly where it comes from. We must first think about the geometry of an atom. Imagine the space around the nucleus as a series of hollow, spherical layers, much like the layers of an onion. We start with the standard geometric formula for the volume of a solid sphere, which is V equals 4/3 pi r cubed. However, we do not want the volume of the whole solid sphere. We only want the volume of one incredibly thin onion layer, or shell. To find this, we take the mathematical derivative of the volume with respect to the radius r. This gives us dV equals 4 pi r squared dr, which represents the tiny volume of that thin spherical shell. Continuing from our volume derivative, we can now piece together the final equation. The total probability, which we call P, of finding the electron inside this specific thin shell is simply the probability density at that distance multiplied by the volume of the shell itself. So we write P equals psi squared times dV. By substituting the expression we just derived for the volume of the thin shell, dV, into our probability equation, we arrive at our final destination. This gives the final result. P equals 4 pi r squared times psi squared times dr. This mathematical reasoning shows us exactly how the geometry of the atom and the quantum wave function combine to give us the probability distribution plots we use in chemistry. With our probability formula established, we notice something strange when we graph it. The probability does not always drop smoothly to 0. Sometimes it hits exactly zero and then goes back up. These regions of exactly zero probability are called nodes. Think of a node like a dead zone in your house, where the Wi-Fi signal drops completely to zero, even though there is a strong signal in the rooms on either side of it. An electron can exist on one side of a node and on the other side, but it will never be found exactly at the node itself. This is a direct consequence of the wave-like nature of electrons. There are two types of these dead zones: radial nodes, which are spherical glass-like shells, and angular nodes, which are flat planes slicing through the atom. To predict where these spherical dead zones occur, we use a simple formula based on quantum numbers. The number of radial nodes is calculated as n sub r equals n minus L minus 1. Let us break down these symbols. N sub r represents the number of radial nodes. The letter n is the principal quantum number, which tells us the mean energy level or shell of the electron, like 1, 2, or 3. The letter L is the azimuthal quantum number, which dictates the shape of the subshell, where 0 is for s orbitals, 1 is for p orbitals, and so on. Physically, as the principal energy level increases, the number of radial nodes increases. This means the electron cloud gets split into more concentric layers, much like a jawbreaker candy with multiple colored rings. Moving from spherical nodes to planar ones, we have a remarkably simple formula for angular nodes. The number of angular nodes, n sub a, is exactly equal to L, the azimuthal quantum number. This formula comes directly from the geometric shape of the orbitals. Because L dictates the shape, it completely controls the angular dead zones. For example, all s orbitals have an L value of 0, meaning they have 0 angular nodes because they are perfectly spherical. All p orbitals have an L value of 1, meaning they have exactly one angular node, which is a flat plane slicing right between the two lobes of the dumbbell shape. If the L value increases, the number of slicing planes increases, creating more complex orbital shapes. Now that we have formulas for both types of nodes, we can easily find the total number of dead zones in any orbital. The total number of nodes, which we call n sub t, is found by simply adding the radial nodes and the angular nodes together. So n sub t equals n sub r plus n sub a. This equation represents the complete set of regions where an electron cannot exist for a given energy state. If either the principal quantum number or the azimuthal quantum number changes, the balance between radial and angular nodes might shift. But this simple addition will always give you the total count of 0 probability regions in that specific atomic orbital. Before we move on, let us see this with a concrete example. We need to calculate the total, angular, and radial nodes for an electron located in a 3p orbital. This is a fundamental exercise to ensure we understand how quantum numbers dictate the physical shape of an electron's territory. First, we extract our given values from the name 3p. The number 3 directly tells us that the principal quantum number n is 3. The letter p corresponds to an azimuthal quantum number L of 1. Remember the sequence? S is 0, p is 1, d is 2. With n equals 3 and L equals 1 identified, we are ready to plug these into our formulas to find the dead zones. Continuing with our 3p orbital, we apply our formulas step by step. First, the angular nodes equal L. So we have exactly one angular node. This means there is one flat plane slicing through the nucleus. Next, we calculate the radial nodes using n minus L minus 1, which is 3 minus 1 minus 1, giving us one radial node. Finally, adding them together, 1 plus 1 gives us two total nodes. Physically, this final answer means that a 3p orbital has two main lobes separated by one planar node. And each of those lobes is split into an inner and outer section by one spherical radial node. The math perfectly matches the physical geometry of the atom. Having just calculated the total nodes by adding them up, you might wonder if there is a faster way. Let us derive a direct formula for the total number of nodes. We start with our basic addition. Total nodes equals radial nodes plus angular nodes. Next, we substitute our specific formulas into this equation, giving us n minus L minus 1 all plus L. Notice the mathematical reasoning here. The negative L from the radial formula and the positive L from the angular formula cancel each other out perfectly. This gives the final result. Total nodes equals n minus 1. This profound truth shows that the total number of dead zones depends only on the main energy level. A 3s, 3p and 3d orbital all have exactly two total nodes because they share the same principal quantum number. To truly grasp what these nodes mean, let us look at this diagram showing radial probability plots for 1s, 2s and 3s orbitals. On the vertical axis, we have the radial probability, and on the horizontal axis, the distance from the nucleus. Look at the top curve for the 1s orbital. It has a single smooth peak and no nodes. Now look at the 2s orbital in the middle. It has one radial node where the graph touches the zero line, which forces the curve to create two distinct peaks. The 3s orbital at the bottom has two nodes, creating three peaks. This diagram teaches us a highly useful rule of thumb. The number of peaks in a radial probability plot is always exactly equal to the number of radial nodes plus 1. Armed with our new visual rule of thumb, let us tackle a slightly more advanced application. We need to determine the number of radial nodes for a 4D orbital and predict exactly how many peaks will appear on its radial probability distribution plot. What is given is simply the orbital name, 4D. Our strategy is to extract the quantum numbers, calculate the radial nodes, and then apply our peak rule. First, the number 4 indicates that the electron is in the fourth principal energy level, so n equals 4. Next, the letter D corresponds to an azimuthal quantum number of 2, so L equals 2. We now have the exact values needed to solve the problem. Continuing with our 4D orbital, we substitute our quantum numbers into the radial node formula. We calculate n minus L minus 1, which is 4 minus 2 minus 1. This math reveals that a 4D orbital has exactly one radial node, meaning there is one spherical dead zone inside the orbital. To find the number of peaks on the graph, we simply add 1 to the number of radial nodes, giving us 1 plus 1 equals 2. The physical meaning of this final answer is that if you were to draw the radial probability plot for a 4D orbital, you would see exactly two peaks separated by a single point where the line touches zero, with the outermost peak being significantly taller. You might wonder why we spend so much time calculating nodes and drawing these bumpy graphs. The reason is that probability distribution plots are the absolute foundation of chemical bonding and reactivity. When two atoms come together to form a molecule, they do so by overlapping their electron clouds. If we do not know the shape of these clouds, where they are dense and where their dead zones are, we cannot predict how they will overlap. For instance, if an atom tries to bond by overlapping with the exact location of a node on another atom, no bond will form because there are no electrons there to share. Furthermore, the outermost peak effectively determines the physical size of the atom. Understanding these plots allows chemists to predict how different materials will behave in the real world. To wrap up our lecture, let us review the key takeaways. First, because of the uncertainty principle, we use probability distribution plots to map the likelihood of finding an electron in space. Second, the radial probability distribution balances the growing volume of spherical shells against the shrinking wave function to find the most probable electron distance. Third, we learned that nodes are dead zones of zero probability, split into radial and angular types, and that the total number of nodes depends entirely on the principal energy level. Finally, these concepts are not just abstract math. They are the essential tools we use to predict chemical bonding, atomic size, and the 3D shapes of molecules. You now have a solid understanding of the fuzzy architecture of the atom.